Thank you for joining the webinar today on decision rules. I'm going to start off just by giving a little background about Morehouse and what we do. Morehouse is a manufacturing company that produces force calibration equipment and adapters that are used around the world to measure force. We're in the risk reduction business for force and torque calibration, and often we have hard discussions with customers who may be confused, frustrated, or don't know about the importance of their measurements. At the end of the day, we've really done our job if we can help someone improve their measurements, which really goes into the purpose of Morehouse. Our purpose is to make a safer world by helping companies improve their force and torque measurements. So if you were to visit Morehouse, you would see our calibration laboratories. We have two. One of them is a force primary standards laboratory, and we offer deadweight calibration up to 1,200 pounds of force known to within 0.002% of applied force. We also offer other force calibrations up to 2.25 million pounds or 10 meganewtons of force known to within 0.01% of applied force. We also have the second most accurate torque standard in the world, which was produced from the National Physical Laboratory in England. And for torque, we have uncertainties of better than 25 parts per million. So for our presentation today, our presenter is Henry Zumbrum. He has been the president of Morehouse since 2013 and has worked at the company for more than 20 years. He really has a passion for measurement accuracy and reducing risk associated with measurements that impact the safety in our day-to-day lives. One thing I've learned from Henry is just about the far-reaching impact of force measurements from everything, the planes we fly in, the bridges we ride on, and the cars we drive. So now I'm going to pass it over to Henry to tell us about decision rules.
All right, thanks, Heather. And as we said earlier, if any questions, we'll answer them, type them in the chat. We'll mention them at the end. So, abstract for today. Many discuss decision rules, and yet not many truly understand what decision rule is or how to use a decision rule to determine the appropriate level of measurement risk for equipment. This presentation is going to cover decision rules, some from NCSLI ANSI Z540.3 handbook, as well as other risk-based thinking concepts. We're going to discuss TUR, TAR, and why requesting a 4-to-1, N-to-1, or whatever the requirement is might not be enough to adequately capture the risk. And then ILAC G809 2019 guard banding will also be discussed. Participants will review examples of specific decision rules and learn what criteria impacts those rules the most. We'll discuss ILAC G8 as well as several documented decision rules and use an Excel spreadsheet to help calculate measurement risk. That was at the beginning. Heather has put that in the chat. Those that are watching this later, they can, the QR code works whenever. You can still grab it. The link to that spreadsheet, just pause the screen, grab the QR code, you'll be good. And that'll be at the end of this presentation. Some definitions, we need to make sure we're all speaking the same terminology. We have specification limits. A lot of times someone will send a device in and say, hey, this is accurate to plus or minus 1% of full scale, or plus or minus 0.1% of full scale. The definition, people use specification limits, they use accuracy limits. The VIM, if we go look at the VIM, you're going to see it references tolerance limits. So everybody knows we interchange the definitions, just so everybody knows. If I say specification, tolerance, it's fine. Measurement quantity value is the quality value, quantity value representing a measured result. Acceptance limit. So what we typically have, we're going to have a LSL or an LS, lower specification limit, upper specification limit. It can be one-sided. Most instruments that we see generally, if this audience is for force, have dual-sided, meaning you have an upper and lower specification limit. Then we're going to discuss guard band, and that's an interval between a tolerance limit and a corresponding acceptance limit. And decision rule. Decision rule describes how measurement uncertainty is accounted for when stating conformity with a specified requirement. And then IEC 17025 says same thing, how measurement uncertainty will be accounted for when stating conformity with a specified requirement. So this is important because how measurement uncertainty will be accounted for. We're going to discuss this in detail, and then test uncertainty ratio, the ratio of tolerance of the measurement quality divided by 95% expanded measurement uncertainty of the measurement process. We're going to go over all these, go through that. The agenda, things we're going to discuss, method 5 versus method 6. I might veer off and talk a little bit about other things. So to start, what is guard banding? The term guard band or uh, sometimes it's spaced out like that and sometimes it's together, appears to have its origins in the early days of radio, when the band of frequencies expected to be utilized by two radio channels or stations were separated by a band of frequency that served to guard against mutual interference by the two channels. It's a nice graph here. So why do you do that? I mean, I really think it would be cool to have Johnny Cash blended in with Rush, the band Rush. And I say the band Rush because recently, if anybody's a Rush fan, Neil Peart died, the drummer died, which is an excellent drummer. Though they have a song called "Free Will," and that song's appropriate in context to say, "If you choose not to decide, you still have made a choice." Is the lyric in that song, and we'll talk about that a little later in regard to decision rules. So if you choose not to account for measurement uncertainty, or ignore measurement uncertainty, you still made a choice, and you might have a very, very high level of risk if you're making that choice. Or you may not understand what shared risk means or simple acceptance really means. But yeah, that's as far as guard banding, early radio days. And what we're doing with uncertainty, we're doing the same thing. We're saying, hey, let's use a method to ensure our risk level does not exceed X. So as used as a national standard, a guard band is used to change the criteria for making a measurement decision, such as pass or fail, from some tolerance or specification limits to achieve a defined objective, such as a 2% probability of false accept. The offset may either be added to or subtracted from the decision value to achieve this objective. Lots of interesting topics here, but this is a good one. Here, I like this picture. ILAC G8 has a lot of graphs and a lot of figures, I guess I should say, and it shows things. And here's a situation where it's showing pass and fail criteria. The use of guard can reduce the probability of making an incorrect conformance decision. It it is basically a safety factor built into the measurement decision process by reducing the acceptance limit below that of the specification tolerance limit. This is often done to account for measurement uncertainty as described later. Here we have an interesting situation. We have a clear-cut pass if we're reading this, right? We have a clear-cut pass right here. Now here we have our whiskers at the top. We have our measured value, which is our dot, and we have our whiskers at the top. And here we have something interesting because a percentage is hanging outside of the specification limit. And then a larger percentage is hanging outside of the specification limit. And then a very large, then the whole thing, everything's out. And this is where we get into what's called indeterminate. So conformity assessment, or like I like to say, it's not black and white when we get into situations where we take the measurement uncertainty into account and everything's inside the specification limits versus some things outside. So when we say 2% risk, what we're saying is only 2% of this is going to hang out. And from this picture, more than 2% is hanging out. So we look at this, that we get into indeterminate situation where this is a pass for sure, right? This is, per the new ILAC G8, this is a conditional pass. You may report this. I'm not a big fan of it because I think we need to report the appropriate level of risk. This is a conditional fail. Hey, it still may be good, and this is a fail, which we'll see a picture later to the points of all of this. So why would you do this? And NASA has a good saying here. It says false accepts can result in reduced end item function or capacity, mission loss or compromise, loss of life, damage corporate reputation, warranty expenses, shipping and associated costs for returned items, loss of future sales, punitive damages, legal fees, and then that's from the NASA publication 1348. In fact, it's around the holiday time, and we were thinking about a Grinch or a MU inch scenario where the Grinch comes in and he steals the contributors to measurement uncertainty, and then all the labs start making measurements. Equipment fails, and the lawyers get rich because us as the consumer, when that product reaches us and it's failing and we have loss of life and everything else, we get litigious and we sue the big corporations, and then the lawyers end up getting rich. But when we look at that and we look at these are important, that's simplified, but it's very important to think about this. What is a false accept and a false reject? And what's the consequence of the false accept? If we don't account for measurement uncertainty properly, or if we don't understand how much risk we, as the end user, not as the calibration lab, as an end user, are subjecting ourselves to, that's a problem. So we have false, people might have heard of type 1 and type 2 error. You might have heard of consumer and producer's risk, but false accept and false reject concepts can be simplified. All measurements have a likelihood of calling something good when it is bad and something bad when it is good. The reader might be familiar with the terms consumer and producers. There's, type beta, type 2, or alpha, type 1 error. And then what's important is we can never know. If we look at the other webinars, you watch the other webinars, we can never know the actual value of the measurement, what we're measuring. There's always some probability that a measured value falls in with an acceptable region when the actual value lies outside that region. This results in our false accept condition. There's also some probability that a measured value falls outside an acceptable region when the actual value lies inside that region, and that's our false reject condition. National standard recommends compliance testing should control false accept risk to be no more than 2%. False accept and false reject risk are only one part of a full risk acceptance. So we look at that and you say, we talked about consumer risk, but consumer risk refers to a supplier of a product assuming a product meets all applicable requirements. That's our tolerance. And then passes the risk on to the consumer who assumes the risk. So we say something's good when it's actually bad. It goes out. It could be a tire. So think about this. So a tire, what does that mean? What are people thinking of when I say a tire? Are you thinking of a car? Or are you thinking of a bike? Because if, still bad, but if it's a bike tire, what are the consequences? Probably not nearly as bad as a car tire, right? So we send faulty tires out all over the world, and then people are driving on the highways and riding their bikes, right? So a lot different when you're driving at 65, 55, 65 miles per hour, or, the equivalent in kilometers per hour. A lot different scenarios if that tire shreds and you're on a highway. So we do not want that to happen. So if that product does not actually conform to the stated requirements, the consumer or the end user assumes the risk. That's us. We bought the tire. We thought the company made good tires. So, and then a further example, if we under evaluate our measurement uncertainty to be used in that decision rule, if we leave out key contributors, what's going to happen? And we'll talk about all of that. So PFA, that's probability false accept, estimate methodologies. That's page 52 of the Z540.3 handbook. If you're an NCSLI member, a plug for NCSLI. If you're a member, that handbook is available for free to download. So you can just go to the NCSLI website and get it. Membership is very inexpensive. They have even 3-year terms. I think it's like $200 for 3 years. And the resources, if you go on there, the documentation that you can grab and read and learn from is well worth it. So the estimation of probability of false accept is a statistical process that depends on relevant data, characteristics of the calibration process, and mathematical analysis. Now, this risk or these decision rules that it seems to be, I go to the trade shows, I look, everybody's talking about them. It seems to be what people are talking about now. For the last decade, it was measurement uncertainty, and now it seems to be migrating towards decision rules. The purpose of this slide is to show they were already there. It was a requirement of the standard back in 2005. And this specific section was 510.4.2. It says when statements of compliance are made, the uncertainty measurement shall be taken into account. That's a shall. It was there. Just takes forever in our community uh, to bring these things, because now we're talking about them. And we're talking about them because the 2017 standard, specifically in 7861 and 782, now they're saying, hey, instead of just taking measurement uncertainty into account, now we shall document the decision rule employed, taking into the account the level of risk, such as false accept and false reject, and statistical assumptions. And then 78862 says right there in C, the decision rule applied unless inherent in the requested specification or standard. That doesn't give you the out to not take measurement uncertainty into account. It just gives you the out that says, hey, I'm using a standard and this is the prescribed method, so I can state conformity with this standard. And we look at this, here's two definitions. ANSI back to 2006. Measurement decision risk is a probability that an incorrect decision will result from a measurement. It's an interesting definition. But then in 2017, they added how measurement uncertainty is accounted for when stating conformity with a specified requirement. Very distinct, very different definitions there if you look at it. And then if we graph this, if people are saying, hey, what's this? So this is a simple graph. We basically said, I'm going to go back to using my highlighter. We upper specification limit, lower specification limit, right? And we graph this with the measurement uncertainty, draw a normal distribution, and anything to the left of the red line is risk, because this is our specification limit, right? When we take into account measurement uncertainty, that instrument or the measurements we make can completely, a large portion of that graph can hang outside of that normal distribution, can hang outside of the specification limit. And in this case, this would be your conditional pass situation. Is it okay? Is the customer okay with 30-some% risk in this scenario? I don't know. That's where ILAC G8 comes in. So back to ANSI NCSLI Z540.3. I like this handbook. As I said, NCSLI, you can get it for free if you're online. Some people who implement guard bands are using methods found in this handbook. The handbook has 6 methods for guard bands. They are these: 1, 2, 3, 4. Very difficult to implement. 2, not so much. That requires some end of period reliability. Method 1, estimation, unconditional PFA. You just need a lot for most of the time to simplify it and not get too into these methods. We'll look at method 5, which is based on the expanded calibration process uncertainty, and method 6, which is based on TUR or test uncertainty ratios. So part of the contract in 7, if we go back to the ISO standard, part of it is 7861 says, hey, someone sent you something, or they want to send you something in, you need to talk to them about the decision rule. So we know people just send us instrumentation all the time. We're happy to have it. And we said, how do we implement ISOs? How do we implement this? So if people send us something with an accuracy specification, if a customer sends us this and we don't know what to do, we'll talk to the customer. If it's just, hey, just do what you want to do and provide it, by default, we use method 5. And we say that right there in this language, that we use method 5 of the handbook. So you send us a force gauge, a load cell, a crane scale, anything with an accuracy specification, we're going to calculate that calibration process uncertainty that we're going to talk about, and we're going to use method 5. Now, if you want other rules, we can discuss them. right? And this is where there's a disconnect, because I think the people that wrote this standard assume that everybody's going to have this conversation, but not everybody understands all the rules out there. And there's so many rules out there that you could implement, and then the cost to implement programming and everything else. I think there's a lot to be said for that. And that's why we gave the spreadsheet. That, as I said, there's going to be a link to download at the end. It's in the chat. It's a tool. It's a part of the tool of the tool belt. You can use it. You can use it to check things. Also want to make a plug to SunCal, those that are writing things down. Colin Decker. The Sandia Labs wrote this program called SunCal. It is pretty tedious to use, but those that want to give it a go, just do a search for SunCal. It is a fantastic program, and it will do, there's some risk methods, reverse sweeps, uncertainties. I've been diving into it the last 3 or 4 weeks, and I'm nowhere near, I'm just scratching the surface of all the cool things that they built that it can do. So that's another free, and it's free. It's wild, written in, I think, Python, and uses the R language. So statement of conformity. We're back to this. What do? We have to make this statement. We want to make a pass-fail, and we're going back to binary, 2 outcomes. The result is reported conforming with the specification or not conforming with the specification. Here's a clear illustration, right? Here's A. Everything's in, our upper limit, our lower limit, and everything's in. And then there's B, where there's a large percentage, don't know what percentage, but there's a large percentage that's hanging over. Then we get into the conditional accept and conditional reject. Similar to what I showed earlier. A little bit is hanging out. That's a conditional pass. And then a lot's hanging out, but a little bit still could be in. So that's a conditional fail, and then there's a fail. And those that know me know I'm not a fan of this. Not a fan of a lot of things that happen, but that's where we get on committees and do things and try to make the change. And we speak our truth, the truth that we know today, which could be different tomorrow as we learn more. So here's what we ran this. We came up with this cartoon for it because it's really ridiculous, right? The instrument, so we do the calibration. This is a conditional accept. The instrument may be in tolerance, but we're not sure. Cal Lab 2 issues the report. Conditional fail. The instrument is out of tolerance, but it still may be okay for your application. So that's what you're saying. It's like, is it good? You have all this risk. Is it good? Is it okay for your application? So we're going to get into TUR, and we made this video, and I think it's worthwhile to show people.
Decision rules and TUR. When discussing decision rules, we describe how measurement uncertainty is accounted for when stating conformity with a specified requirement. The conformity for most is binary, meaning either a pass or a fail, and some standards recommend setting the limits, so a fail occurs if the total risk is larger than 2%. The laboratory shall document the decision rule employed, taking into account the level of risk. Many of the decision rules found in documents such as the ANSI/Z540.3 handbook and the ILAC G8 use test uncertainty ratio, or TUR, to help calculate their measurement risk. TUR is defined in the handbook as the ratio of the span of the tolerance of a measurement quantity subject to calibration to twice the 95% expanded uncertainty of the measurement process used for calibration. The formula for TUR consists of the span of the tolerance in the numerator. The denominator includes temporary and non-correctable influences incurred during the calibration, such as repeatability, resolution, error in the measurement source, operator error, error in correction factors, environmental influences, and others. We must standardize definitions when discussing TUR because when significant contributors to measurement uncertainty get omitted, every subsequent measurement will be suspect and bad things may happen. When we use the appropriate formula and draw the concept, we draw the lower and upper specification limits at 999.5 and 1000.5. Next, we put in the location of the measurement at 1000.4. The calculated calibration process uncertainty determines the width of the distribution. As you can see, the larger the measurement uncertainty, the larger the risk relating to the measurement location. The smaller the uncertainty, the lower the risk. Such is the case in this example when Morehouse performs the calibration. The ways to reduce the risk are simple. Follow the formula for TUR. Find calibration labs, such as Morehouse, with the lowest measurement uncertainties. Buy better equipment that is repeatable and has enough resolution. Control the environmental conditions. Morehouse manufactures precision force measuring equipment, proper adapters, and has measurement uncertainties 10 to 50 times lower than many, which allows for low test uncertainty ratios to pass more calibrations. Using Morehouse for your force and torque calibration needs can reduce your measurement uncertainty and risk. Call us today.
All right. So hopefully that videos shed some light. Try to make those videos under 2 minutes because people's attention spans aren't what they always are. But no, we're going to reaffirm some of the things that was just shown in that video. So TUR defined, ratio expanded tolerance subject to twice the 95% expanded uncertainty of the measurement process used for calibration. Then ILAC G8 has a similar definition. The thing with this one is the ANSI Z, if the tolerance is not symmetrical, the ANSI NCSLI is much clearer. But if we look at decision rules and we look at definitions, and I've talked about this before, and ANSI Z540 basically says for the numerator, the tolerance used for the unit under test and the calibration should be used in the calculation of TUR. The tolerances to reflect the organization's performance requirements for the measurement and test equipment, and it goes on. Really easy. We have those that don't know or haven't know, follow us on LinkedIn, follow us on Facebook, whatever your method is for following us. We have a blog that's coming out that runs through an example of a TUR calculation. This will also be found in the new chapter of the metrology handbook, to how to really run through this formula. So what's really important here is this definition for the denominator that I have highlighted, because for the denominator, the 95% expanded uncertainty of the measurement process used for calibration following is used. And we've simplified this. We simplified this formula from what's below, which basically says influence of the item being calibrated, except for the bias of the M&TE, the calibration process error therefore includes temporary and non-correctable influence incurred during the calibration, such as repeatability, resolution, and error in the measurement source, operator error, error in correction factors, and environmental influences. All these are very important. However, if we are accredited, we need to comply with ILAC P14. So when we're doing our CMC, our calibration and measurement capability uncertainty, there's a section in ILAC P14 that says contributors to the uncertainty stated on the calibrator shall include relevant short-term contributors during the calibration and that can reasonably be attributed to the customer's device. So if we look at that formula for ANSI Z540.3 handbook, a lot of this should be really wrapped up in the CMC calculation of the different operators and everything else. So what we've done is we've simplified it down to, hey, we're making an assumption that people have done the CMCs correctly, and then we're saying, hey, what if we're going with ILAC? We have to go. If we're accredited, we have to go with ILAC P14. So how do we make this formula work for ILAC P14? We say, okay, there it is. Uncertainty shall cover the same contributors that were included in the evaluation of CMC. Yep. Except the uncertainty component's value for the best shall be replaced with those of the customer's device. Therefore, reported uncertainties tend to be larger than uncertainties covered by the CMC. So we have to add. And it says short-term contributors during calibration and contribute that can so those short-term ones are resolution, repeatability, and then we added other error sources to capture the environment and just a catch-all. And we have that in the download on the PFA. So we need to grab that. If we're going to do that calculation, we're going to calculate our calibration process uncertainty, which is our measurement uncertainty, really at the time of calibration. It includes all the contributions from the unit under test, that's a good formula to use. So the calculation of TUR, people get this confused because there are documents out there that say if you have a 4-to-1 TUR, if you have this, you don't need to worry. Be careful with those documents because a lot of them don't tell you the fine print, right? And the fine print is that assumes that there's not bias in the measurement. That assumes the measurement is perfectly centered on the graph. You don't see that often. In fact, the book Introduction to Statistics and Metrology, another great book, and that's Introduction to Statistics and Metrology, talks about that, and they put it in. They put the blurb in that when they wrote this, they thought about it, and they make the statements of a 3-to-1 TUR, a 4-to-1 TUR, and they do not consider the measurement bias. So just remember that when you're looking at those other standards and someone says, hey, as long as it's 4-to-1, yeah, as long as it's 4-to-1 and the location is centered. They don't add the and. So the denominator is useful in the TUR calculation to do other things. We can use it for method 5. We can use it to calculate our expanded uncertainty that we can report on our scope. So very useful, that denominator formula. So ILAC G8 can be used for that. ILAC G8 is a little bit different than ANSI Z540.handbook because ILAC G8 method says, hey, a PFA of less than 2.5%. ANSI Z540 says 2%. When used in combination with a measurement, one can calculate measurement risk at the time of calibration. So we'll start reviewing some things here. Global consumers risk. This is defined in JCGM 106. And it's the role of calibration process uncertainty, that's CPU, in conformity assessment. That's our denominator of the TUR equation, just so we know. And it's the probability that a non-conforming item will be accepted based on the future measurement result. Go back to our tire situation. Go back to we have a tire gauge that was calibrated, and someone said it was good when it was actually bad, or non-conforming. Someone said it was conforming when it was actually non-conforming, and that's used on things. So we keep passing that down. If that's used as a comparator for something else, because calibration, we compare something that's within a relatively known quality that we know with something that's probably not known, and we do the comparison. So if we make those wrong decisions, it's going to go the whole way down the chain. So if we go to an NMI, if we send a device to an NMI and they make a mistake, it's going to go down. That's going to impact us. We do cals for you. That's going to impact you the whole way down. So wherever that mistake occurs, it goes the whole way down. So if only one tier of the calibration chain cares about the measurement decision risk, then the whole process is at risk. When the risk is properly propagated throughout succeeding tiers, can we expect the process to work properly? We can't. Eventually, it's going to fail. So some users may not understand the decision rule and what it means for them. We have not had enough discussions or questions regarding decision rules to grasp who really understands them. That's a biased statement coming from me and just being out there asking questions. And then was written around risk. And yet I feel many expect a statement that says pass with a sticker that allows them to use the device to make measurements. And that's the sad part of it. As we start to learn more, we see, well, how are you making your decisions? What are you doing with your customer? Some people say, hey, should we just do simple? Is that okay? I just want it based on our tolerance or specification limits. If you do that, you have shared risk. And like I said, I try not to go too far in detail with all of these things. But what I want to show here is if we look at this and we look at things like, hey, if we start to omit the formula or cherry pick that formula and say resolution's not significant, let me ignore it. Right? This is a specific example where I just ignore the resolution. So you can see the graph here. And you have TUR with and without resolution, right? Without, if I just do a simple calculation, a TUR, I could use a test accuracy too. I could use all kinds of stuff. And if I don't put the right stuff in the denominator, it's just going to stay the same. But if I put repeatability, in the denominator, I put other error sources in, and then I put resolution in, it's going to change. Right? And this graph shows what happens. As the resolution of a device increases, the test uncertainty ratio decreases. And then this came from a paper that Scott Mims wrote with this example. When the resolution is considered, the TUR starts at 6.25 with the UUT resolution of 0.001 kgf and then declines to 0.117 to 1 with a UUT resolution of 1 kilograms of force. So when resolution is not accounted for, the TUR ratio stays at 6.25 regardless of the resolution. If a calibration laboratory uses something like test value uncertainty, which is in another standard, then the UUT's resolution could be ignored in the conformity assessment. Just a risk. In fact, I mentioned the paper Scott Mims wrote. It's the importance of decisions, and he uses a micrometer example in there. This is our example from a load cell. So taking measurement uncertainty into account, here's ILAC G8. It's a free document. You just type in ILAC G8 2019. You can go download it. You can work through it. But here's some different guard bands. Decision rule, 6 sigma, 3 sigma. ILAC G8 2009. I like that rule. That's less than 5. ISO 1423. I believe you have to buy that standard. Simple acceptance. Talked about that. So what that is, and I hope people know what that is. But when we talk about simple acceptance, that just means you send a device to a calibration laboratory and they make a decision based on the specification limit. They do not take measurement uncertainty into account at all. Here's that 0. And when they do that, you could have up to a 50% risk. Because if your specification is plus or minus 5 pounds, and the lab that's making the measurement says your measured value reads plus 5 exactly, there will be 50% risk that you absorb. And we'll talk about that. So ISO requires laboratories evaluate measurement uncertainty and that they apply a documented decision rule. When a customer actively manages calibration intervals, as mentioned here, during contract negotiation with laboratories for services compliant with 17025, they can direct the laboratory to use the average global risk associated with decision rules when reporting results per clause 7.822. That whole, some customers do that. I don't see many in industry doing this. And then where choices of decision rules are available, customers and laboratories will need to discuss levels of risk regarding the probability of false accept and false rejects associated. No single decision rule can address the diverse scope of testing and calibration covered. So there's so many variables here, and that's what people need to decide. You have, we talked about the ILAC G8 rule. You have, here's method 6 that we're going to talk about now. The pros and cons of these two methods. I do happen to like the standard. First, it's free. All these are ILAC G8's free, and the handbook. If you're a NCSI member, you can pull it. But method 6 in the handbook. This is a less conservative approach. It's simple to calculate, and it depends on the measurement uncertainty when compared with the specification limits of the unit under test. This is where it's critical because it uses TUR. And then we have guard band method 5, and that's based on the expanded calibration process uncertainty, which is the bottom of the equation. And it's another simple approach. It's basically recommended by G8, but they opened the limits up a little more, and you can look at that. And we look at this, it's interesting because the people that wrote the 2% PFA requirement, it was in an email. It's so funny how things happen. Emailing somebody and they were talking to me, he said, you know where that 2% PFA requirement came from? I don't. I really don't. But I do know, and I'm going to show you that ANSI Z540.3, I found this pretty interesting. They wrote the standard and they used the probability, they used a confidence interval of 95.45%. This basically responds, in most cases, has a coverage factor of K equals 2. So when you do this math, it's not 2%. They rounded down. So if this is all showing what's going on. So if I use what ANSI Z540.3 says, a 2% PFA, it basically says, hey, if I subtract the uncertainty, my risk should be less than 2%. And when I do that, guard band, lower specification, and upper, and up here I plugged in the measured value. I'm going to switch to a pen because I already have this highlighted. So what I did is I said, okay, let me just subtract the uncertainty. Let me plug this value into the equation, 9.96002. And we look at this, and our total risk is 2.2, and if I would have carried it, it would have been 2.275. Therefore, they rounded it down. So when you hear 2%, be a little skeptical. If you're using method 5, it's actually a little bit rounded down. And then if we wanted to calculate it, and our sheet allows you to type in the appropriate level of risk that you want, that PFA sheet. If you wanted to calculate it, if the requirement really was 2%, you'd have a little more room, so to speak. So let's look at these examples. Method 5 versus method 6. So method 6, something to be aware of is it may not calculate acceptance limits correctly with very high TURs. So you have to, if you're using method 6, you kind of have to modify the formula here. This is an example showing a super high TUR, 85.16, and it's basically saying your acceptance limit is above the specification limit. That all goes away with simple math. You just say, hey, if my TUR is 85.46, you write like an if statement. If my TUR is 85.16, use a TUR of 4.5, and then it'll work correctly. So we built that into the sheet, but that's not this. I'm not aware how. I'm not aware of many places where that is actually discussed, but it's built into the sheet. You can see it. So method 6, some call this the Dobert method, uses this formula. It calculates an acceptance limit of 2%, tolerance limit minus that 95% calibration process uncertainty, and then it uses this other multiplier, provides a guard band to ensure 2% PFA. It basically tells you, are you in or out? And if you're in the acceptance limit that's calculated, the risk is less than 2%. It's a great method. Here's some raw data that we have, just looking at different points, average instrument reading. So if we did a load cell, someone said, hey, I have a 10,000 pound device. Let's do 3 runs from 1,000 to 10,000, and we found this to be, that's just average data to do some comparisons with. So, and then we got our average data, and then the customer says, I need my tolerance to be 0.05% of full scale. So we run both methods. And if you see both of these methods, you can see method 5, where we're subtracting that calibration process uncertainty, really, and then we're versus method 6. And one of them is going to say pass the instrument, and the other one's going to fail. That's being, this method 5 is very, very conservative. If a lab passes you under method 5, that's a conservative method. We find a lot of people want that reassurance under that method. And I don't know if that's just uneducated customer base, or if it's educated customer base that says, I don't want any risk. I don't want you to pass any risk to me. Use a conservative method and adjust it if need be. Don't know. However, if we look at these two, method 5, method 6, if we change the CMC, this is looking at these contributors, the different contributors. And if we change the CMC, right here we're using dead weight. What if we change it to like 0.5? What happens, right? So 0.5, more fail on method 5, and on method 6, some start to fail. Why this is important? Because we've now applied a decision rule. We haven't just done simple acceptance, because with simple acceptance, honestly, almost any laboratory can apply something and pass it. Now, they are required, if they're accredited, to report the measurement uncertainty, and the measurement uncertainty should not be greater than what they're calibrating, but there's still a whole heck of a lot of risk with that. So when we use the formula correctly, we see the true picture, right? And this true picture is, hey, with these measurements, if I made these same measurements and my measurement uncertainty was higher, I would not be able to pass the instrument. So that's with the tolerance of this. Then we're going to say, hey, right here, now we're going to raise the tolerance. So I used the lab that was 05. I want a conformity assessment. They're failing it, so what do I do? Well, maybe you need to change your tolerance. If everything's failing on the decision rules, this is a probability that you might need to change your tolerance. And manufacturers don't always get this, right? They sell an instrument, they say this, they say that, but are they all, or do they all have metrologists that understand these decision rules? And I can answer, not all of them do. Many of them have really good ones, the big name manufacturers. We all know their names. They're making multimeters and stuff. Fantastic people that work for them. Learn a ton. So this is what it's saying, right? Those pictures, this is a picture that shows, is probably worth 1,000 words right here. It's basically saying I use that small relative expanded uncertainty, and my acceptance interval is a lot larger than when I use the small uncertainty. That's all we're saying. So with this, using the dead weight, I have more room, more wiggle room from each side to be in. And we'll show that in more detail. Here's calibration process uncertainty, Morehouse dead weight, 10,000 pound cell. TUR, we look at this, TUR 13, calibrating the TAR, which we haven't discussed. That's test accuracy ratio. I don't like that at all. But that's 62.5. And CPK is a concept I'm going to talk about because that really gives you some insight on the measurement location. And that's built into these sheets as well. So here we have our specification. We do the calibration. The measured value is 10,008. And if we do 2% risk, if we allow for 2% risk here, we can be between these two numbers, right? 9990, really the instrument reads by 0.1. So it's really 990. No, I'm sorry, the instrument reads by 1. So really we can be in within 991 to 10,009. But those are the two calculated that we can be at. We go to the 05% uncertainty. Now everything goes up. That same instrument, same measurement at 10,008 that we called good, if we use, or we switch to a secondary standard, we switch to a calibrating machine. The dead weight machines are busy all day. And we switch to a calibrating machine. We don't do that. If we say on our quotes, if it's dead weight and you get dead weight, but if we did, the risk would go up. We couldn't make a conformity assessment, right? Depending. I mean, if you sent us a contract that said, hey, we need our total risk to be less than 10%, we could make it. If you said we need to be less than 6.2, we could make it. Most people are going to say 2.5 or 2%. They're going to go by the standard. And then what happens when a lab asks for a TAR or TUR 4-to-1 or some other arbitrary number? It's what happens. Some say, okay, if I send this to X lab and I know my TUR is greater than 4-to-1, we're good. And here's that example I was talking about. When it's on the specification limit, right? Here, our measured value right here is right on the specification limit. TUR is 16.69. TAR is 62.5. CPK went to 0. And look at the risk, 50%, no matter what. This is not taking measurement uncertainty into account, right? That's what it is. So if you do not consider the location of the measurement, you may not be considering risk properly. And here we just moved with that TUR of 16.69, we just moved the measured value over to bump it back in specification to show. So if you look at those here, it's on the line, it's bad. If we slide it over just one count, it would be in. Huh? adjust, not adjust. Just really important to analyze this, and CPK is a good tool to do that. So TUR assumptions, using a TUR assumes that all measurement biases have been removed from the measurement process. We're showing you here that what the assumption is, and people really doesn't happen from the measurement process, and the measurements involved follow a normal distribution. If there are significant biases that cannot be removed, the TUR will not account for the increased risk. So we got to remove them. And CPK is a useful tool to use with TUR and account for the location of the measurement. So more about CPK, because I really think this is a good tool that like more and more people will start looking at. CPK, process capability index, used in statistics, used for a lot of manufacturers to say, hey, if my CPK is this, then I'm making product, and if it dips below this, about 14% of my product's bad, and they run numbers and calculations based on it. But it's for our purposes, if we use it, it's how close you are to a given target and how consistent you are to around your average performance. And it measures two things very well: how close the mean of the readings are to the center of the lower and upper spec limits, and how widely spread the readings are. So if we look at this, just simple numbers, if the CPK is less than 1.33, it might need some action. You know, different vendor with lower uncertainties, better resolution, adjustment to the instrument, a more repeatable process. If CPK is higher than 1.66, then everything is good. So 1.66, yeah, nothing needs to be changed. At 1.33 and below, you could still be good. It's just a tool, right, that would let you know. And if we go back and look at where we were on some of these, there we had a CPK of 2.21. Look at the location right here. It dropped to 0. That's a flag. How close are we to approaching that lower specification limit? Here, the CPK was 0.51 with a 6% risk, right? 1.833, you know, again, above that 166 number, and we had 0 risk. So very, very useful tool in calculating risk and giving you insight into the risk based on the location of the measurement. And here's a cartoon we did about TAR. You saw in all those examples, the TAR was super high. TAR doesn't do much of anything. And people still use it. It's outdated. It's not sustainable. It's the ratio of accuracy tolerance of the unit under calibration to the accuracy tolerance of the calibration standard. It's just quick, easy. It was supposed to be temporary until better computing power became available. This was said in like the 1950s, people. So I would think better computing power is better than the 1950s. I would think we could all get agreement on something. I know everything's polarized and no one agrees on everything anymore, but that one, I think that our computing power is better now than the 1950s. We would get 100% agreement on. Heck, our cell phone does more than what we had in the 1990s. That we carry in our pocket. So before ANSY's explicit defined the equation for TUR, many were using TAR and TUR inconsistently. Look, they still use it inconsistently. At least now we have something to educate to. We have ILAC P14 that you combine with G8, that you combine with ILAC G8. ILAC P14 is policy, needs to be followed. G8 is guidance. You have ANSI Z540.3 handbook for decision rules and methods, clearly defining that calibration and process uncertainty. So we can all use the same thing. Maybe different labs use other error sources a little bit differently. Hopefully we all calculate our measurement uncertainty properly. If we don't, and if you need help with that, visit our website, the Excel section, the documents and tools section. We have Excel tools and guidance documents to help with that as well. And many in the metrology community have invalidated TAR because it does not align with metrological traceable practice or account for measurement uncertainty. Some people say we've considered our risk because we've looked at TARs. Have you looked at location of the measurement? Have you looked at all the other stuff? So here's why. Measurement decision risk, the importance of definitions. There's a paper. You just Google it. Great paper, great reading. I encourage anybody I ever run into in metrology to run into it. And he provides an example in there of a digital micrometer, because I don't want to use everything with force. Giving a 25 to 1 TAR ratio And then he compares that with the definition of TUR found in the ANSI Z540.3 handbook and produces a 1.5 to 1 ratio on this for the same measurement. We were seeing that earlier. And here's why it's not sustainable. Test accuracy ratio in a closed system could work. I don't want to get too far into it, but look at this. So I said I have my measurement and it's saying, hey, okay, this measurement I need to be 4 times better than this. And then I need to be 4 times better than that. So it's 16 times better than my process measurement. Then I need to be 4 times better than that. So now I'm 64 times better. Now maybe it's traceable, trace to SI through NIST. Maybe. So now NIST has to be 256 times better. Oh, and don't forget the SI, where the units, or the BIPM, where we're likely going to send, if it's the prototype kilogram, we're going to send it to the BIPM. They still do that. And it's got to be 4 times better. It's just not sustainable. Is it really 1,024 times greater? Whereas if we look at the current way things are done, measurement uncertainty data is cumulative from one level of the hierarchy to another. So you start with SI, and now NIST has to add the uncertainty contributions from this. NIST has to add it to their measurement. We go out, Morehouse goes out, has our stuff calibrated by NIST. We have to absorb NIST uncertainties. So every point of this gets larger and larger, and every lab is absorbing the uncertainties of the previous lab that had done the calibration. It works very well. This is a little more confusing. That's on the spreadsheet, but what this spreadsheet has so many options, and it'll allow you to vary like repeatability conditions and do everything else. So this table was created. We just said, hey, I made some random generators and I said, let's vary the repeatability and resolution only. And we kept our CMC, that's the dead weight that's used. And it said, how good does the reference standard need to be to comply with less than 2% risk? So TAR, again, 62.5 the whole way through. TUR went from 62.5 down to 0.344. And if we look at this, you just look at this table, you can start seeing total risk, where it is. Right here, we start getting some risk based on the capacity and the measurement location and everything else. So it's a table. It allows you to do a lot of different things. And if we look at graphically, resolution and repeatability effects on TUR, why they need to be included, you can start looking at this graphically and you can see how it declines, so to say, when you start increasing them. And then TAR versus TUR. TAR number is always going to be the same. TUR is going to vary depending on, resolution and everything else. So what did we do in this? And we are varying the measurement uncertainty. So here we said, hey, let's assume the device is going to be repeatable and have the same resolution. And then let's just vary this column, this measurement uncertainty column, and see what happens. So in this scenario, if I wanted 2% risk, assuming my measurement is centered, right? This is basically saying I need to find a lab that is somewhere between this 0.01 and 0.02 or better to make this measurement. And you can back calculate what you need to be, but that's what it's saying. Of course, if I want more room, more elbow room, then I find a lab with much lower uncertainty than that. So uncertainty and risk, right? As the uncertainty increases, so does the risk, and that's all this graph is showing here. So is when you have low uncertainties, the risk is very low until you can start to see it creep right here. This is just graphically, you can start to see it here around the 9.22. So ILAC G8 2019, they have these diagrams in there. Good. Conformity decision required, yes, no, legal standard, follow the different guidance, applicable standard, choose the decision rule, zero guard band, TUR. Be careful with this one, right? Hopefully you learned today. Be careful with this one, just saying a TUR is better than N to 1. I know the ASME does some of this stuff. that assumes your location, assumes the biases have been removed from everything that I've read. And the best book to quote on that is Introduction to Statistics and Metrology. So the decision rule, a little bit of wrap up, and then we'll take questions. The decision rule applied should adequately calculate the measurement risk level. If measurement result is governed by legal or regulatory standards or rules, then use the decision rule as prescribed in the appropriate standard. Everyone may have different levels of risk for their application. The Excel tool can help evaluate the risk level and possible decision rule. PFA is also about location, 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 which CPK is a useful tool, and that's that probability of false accept. And the labs with the lowest measurement uncertainty should help lower risk. That said, thank you, everybody. It's been a pleasure. And we will see you. If we don't talk to you or you don't call us or anything else, we hopefully will see you back in January when we kick off some more webinars.